Hello everybody, welcome back to the Exam 2 review video. This is the last video of two. This video is going to be all-encompassing to cover topics of Claisen and Dieckmann condensations, Michael reactions, and Robinson annulation. So without further ado, let's kind of just jump right in. So, as we saw with the last material, we did aldol condensations, and that is essentially exploiting the acidity. Let me zoom back out here. It is essentially exploiting the acidity of these alpha protons. So over here we have an alpha carbon. And then there are the associated alpha protons. We know that these alpha protons are acidic because the resulting enolate or the resulting anion is resonance stabilized. So again, just to bring this back to the forefront of your brain, if we have a generic base that comes in and deprotonates the proton and puts that sigma bond density on the aldehyde skeleton as a lone pair, the resulting transformation will yield a structure that looks like this. And of course, when we take a resonance perspective on this, we can push those lone pairs in to the left towards the carbonyl. We exceed the octet at this carbonyl oxygen, so we're forced to push those pi electrons up. And the resulting structure is an enolate that looks like this. And of course, this is all just showing that we are resonance stabilized. So essentially just me reiterating the fact that these alpha protons are acidic. So what happens when we have something like an ester? So something that may look like this. Well, of course, here we have an alpha carbon. This is the alpha carbon, just like with the aldehydes and ketones. And with that alpha carbon, we have 3 alpha protons. Okay, so alpha protons. Alpha carbon. So my point in showing you this is that esters we would expect to react similarly like aldehydes and ketones do in an aldol reaction. Now, when we think about the acidity of an ester alpha proton, it's slightly different or slightly higher pKa value than the aldehyde alpha protons. So essentially, why is that? We want to make that clear. So when we deprotonate, so let me just show that generic base again. Let me switch colors here. If I showed that generic base again, deprotonating one of the alpha protons, the results of that transformation would be a structure that looks like this. Of course, that lone pair is resonance stabilized. We can push it in towards the carbonyl and forcing those pi electrons up. But keep in mind, the difference here is that we actually have a methoxy substituent instead of either a proton or a generic alkyl substituent if it were a ketone. That methoxy substituent has an effect on the acidity of those alpha protons because the lone pairs on the oxygen actually also participate in resonance to some extent and can be pushed in towards the carbonyl. So if we're adding more electron density into an already negative thing, that's a repulsive effect or a destabilizing effect. So my point is that yes, these react similarly to aldehydes and ketones. However, the acidity is quite different with an ester, and be prepared to rank various alpha protons in terms of their acidity based on different carbonyl functionalities. So an aldehyde, a ketone, an ester, etc. Okay, so now let's kind of jump into the meat and potatoes of what a Claisen condensation is or what a Dieckmann condensation is. So Claisen. So this is all about Claisen and Dieckmann condensations. So what I want you to take away from this video is that Claisen is just aldol, but with esters. And Dieckmann is just the intramolecular Claisen. So we saw with aldol, we can have an intramolecular aldol. However, it does not get a specific name like the Dieckmann condensation. So just keep that in mind. All right, so, before we jump into actual Claisen and Dieckmann practice, I think it's important to talk about a prereq. Okay, so a prereq for Claisen and Dieckmann condensations. We need at least 2 alpha protons, or we need 2 alpha protons. I shouldn't say at least. We need 2 alpha protons. okay? And this is different than with the aldol chemistry we saw before. Aldol, we can definitely promote that condensation reaction with just one alpha proton, but here we need at least two for the Claisen and Dieckmann, and that will become clearer when we do a mechanistic example. So again, let's kind of practice this notion that we need two alpha protons. So before even talking about the reagent conditions, the mechanistic pathway to do these reactions, I'm going to give you a pair of esters, and it's up to you to tell me which one is more primed for a Claisen condensation. So if I gave you an ester that looks like this, and perhaps maybe one more ester that looks like this, which ester is more prone for a Claisen condensation? Well, we're looking for that prereq. We need two alpha protons. So if we look at, this alpha carbon, we see that we have two alpha protons. And then if we look at the right ester, we see that we have this alpha carbon with one alpha proton. So based on that prereq, clearly this is the better ester for Claisen condensation. Let's do one more example of that. So if I were to give you maybe this ester, and perhaps maybe this ester, which one is more primed for a Claisen condensation? Well, with the ester on the left, we see that we have an alpha carbon, and that alpha carbon has one alpha proton. And then with the ester on the right, we see that we have an alpha carbon with two alpha protons. So based on that prereq I described, the ester on the right would be more prone for a Claisen condensation. Be able to do something like this on the test, identifying which ester is better. And likewise, if I were to consider a Dieckmann condensation, let's kind of take an example and be able to circle, the reactive site on this molecule. So if I gave you a structure that looks like this, this is obviously an intramolecular version because two esters are within the molecule. Which alpha carbon is going to be used as a nucleophile in Claisen? Well, we see we have two alpha carbons, alpha 1 and alpha 2. And at alpha 1, we have one proton, and at alpha 2, we have two protons. So this is the reactive functionality. This is the reactive ester, the nucleophilic ester, okay? And now I think it's worth going into an actual mechanistic example and being able to predict the product. So I just want to bring this back to the forefront of your brain. But with what we saw with aldol chemistry, we had this nuance of thermodynamic and kinetic control. So there are two main types, a thermodynamic aldol and a kinetic aldol. And we said with the thermodynamic, we would form an alpha-beta unsaturated carbonyl, which would look something like this, perhaps. And, just to fill in some Greek letters here, alpha and beta. So with respect to the ketone, the alpha and beta position has an unsaturated carbonyl. That is one functionality that we were looking for. And then with the kinetic control, we saw that we formed a different functionality called the beta hydroxy carbonyl. And again, just for some clarity purposes, a beta hydroxy carbonyl would look something like that. And again, let's fill in the Greek letters here, alpha and beta, okay? So the beta hydroxy carbonyl is a different type of functionality. So now with Claisen or Dieckmann, doesn't matter if it's intramolecular, you would still get the same functionality. In Claisen and Dieckmann, we don't have thermodynamic and kinetic control to consider, so we would just know that we are forming a beta keto ester. And what does a beta keto ester look like? Well, if I had an ester, with respect to the beta position, you have a keto. So again, let's fill in those Greek letters here, alpha, beta. This is a beta keto ester. So we're just building here on our knowledge. We're forming a different functionality. I think it's clear that we can see the reactive portions here, the carbon-carbon bonds that are formed, okay, where I'm splicing in between alpha and beta. Okay, notice that the only difference is that we're replacing the hydroxy or the double bond with a carbonyl compound. And then the original nucleophile isn't a ketone or an aldehyde, it's actually an ester. Okay, so slightly different looking functionality here. So now I think it's time to just jump into some practice. So here, let's give you an example. If I had a Claisen condensation reaction that looked like this, how does the mechanism look? Let me predict the product. Okay, so a couple things I want to point out first as I fill this all in for you. Okay, so number one is that there are a different choice of base here. There is a different choice of base here. So notice that with with aldol reactions, we used aqueous bases such as sodium hydroxide or potassium hydroxide. Yes, we also used LDA. But sodium hydroxide and potassium hydroxide cannot be used here because, as we learned in the last exam material, aqueous bases, or basics, can basically hydrolyze the ester in a mechanistic fashion that looks like this, and the resulting transformation results in a carboxylic acid. That carboxylic acid is not an ester and does not have the same reactivity to promote a Claisen condensation like the ester. So that is why we have to use these alkoxy bases. So I think that's the first thing I want to point out. We have to use alkoxy bases. So these are alcohol-based bases. As well, the alkoxy base typically matches the alkoxy fragment of the ester. So by that I mean the ethoxy group on the base matches the ethoxy group on the ester. So just make sure you match those things if you were to provide reaction conditions for this. Okay, so now let's kind of talk about the actual mechanism. So just like I've done before, I am going to just redraw this problem here. There's two equivalents of this, of course, and we're having a base approach. Okay, so step one is those alpha protons are acidic, right? Not as acidic as ketones and aldehydes, as we've just described, but we can form an enolate, just like we did before, and the result is a structure that looks like this. We now have an enolate, or a nucleophile. Okay, just like I've done before, I want you to draw your enolate left to right, where your enolate is the rightmost thing. Anything to the right of that enolate should go down, okay? So a structure that looks like this. So ETO. So I want you to draw your enolate like that. I did not do any sort of mechanistic transformation here. I just pancake flipped the molecule and pulled this extra ethyl group down. 1, 2 is now down. Okay, so just a rotation. Now, if I show the other equivalent of the ester nearby, oops, ETO, I'm going to show nucleophilic addition into that ester, just like we've seen with aldol. Okay, the result is that we have a tetrahedral intermediate. So I'll draw that, I guess I'm running out of space here, so I'll go up. The result is a structure that looks like this. Okay, and then now that tetrahedral intermediate collapses. Here, the mechanism differs slightly. So in comparison to aldol. So when we did aldol and we did nucleophilic addition into the other equivalent of aldehyde or ketone, we saw that we would protonate the alkoxide. We would put a proton here, and we would either leave it if it was under kinetic control as the beta hydroxycarbonyl, or we would go a step further and dehydrate this to form the alpha beta unsaturated carbonyl. Here we don't have protonation, so what we actually have is collapse of the tetrahedral intermediate and ejection of the ethoxide. So the result of that mechanistic transformation is something that looks like this. That's a 1, 2, 3 carbon fragment, so it should look like that. Okay, so we're almost done. So there's a weird nuance about Claisen mechanism, so I'm just going to erase this to make more space. But there's a weird nuance with Claisen condensation. So you formed a neutral beta keto ester here. Notice it's a beta keto ester and beta keto ester. Let me just fill in the Greek letters for some clarity purposes. Alpha, beta, this is a beta keto ester. You formed a neutral product. You think that you're done. However, there is a specific consequence of ejecting this ethoxide group. So ethoxide is the base that you started with, right? And at this step over here, we have just ejected it. And it's still relatively close to the material. So now, what's the consequence of forming this beta-keto ester with respect to the acidity of the alpha proton? Well, now the alpha proton is even more acidic than it was in the ester starting material. The reason that is now we have a double inductive effect. Not only do we have a resonance stabilization or a delocalization towards the ester, but we also have another carbonyl at play that's also helping to stabilize that base. So, stabilize that acid. So the mechanistic transformation is really not complete until you show another enolate of the diketone, or the dicarbonyl. So the result really of step 1 is this enolate anion of this dicarbonyl species. That's why we're seeing step 2 as an acidic workup to reprotonate and form the neutral beta-keto ester. So really, this is the product of step 1. And then the product of step 2 is obviously just a protonation to form the neutral beta-keto ester. Okay, I know I'm kind of drawing all over the place here, but that would be the mechanism for this Claisen condensation. There are some nuances. So if we were to ask for a Claisen mechanism, I need you to show this final ejection of ethoxide and also deprotonation of that remaining alpha proton. A lot of people miss this step in a mechanism, so just don't be fooled there. All right, and then there's a stereochemical consequence, of course, so make sure you keep in mind you do have to draw all possible and major stereoisomers. We did form a chiral center at this carbon, so you'd be expected to draw both enantiomers of the wedge and dash configuration. So I guess for some just clarity purposes, just for you all watching this, I would expect on the test for you to write something that looks like that, as well as the other enantiomer. Something that looks like that. Okay, so that is the answer to this first practice problem. Okay, I hope that helps. Let's try another example. So if I were to give you a problem that looks like this, let's think about how it would react. Okay, so your first hint is to look at both of your esters and find out which one has alpha protons. So if we look at the ester on the left, and we were to look at the alpha carbon, we see that we actually don't have any protons here. So okay, maybe this is my electrophilic ester that we're going to actually add into, have the enolate ester add into. So here we're not going to be nucleophilic. But if we go to the right ester, we also see, maybe it's more clear if I draw in my pi bonds, we actually also do not have any alpha protons at this position. So this also can't be, I'm sorry, I can't get this marker right. We also cannot have a nucleophilic enolate from that ester. So therefore, if I don't have the prereq of 2 alpha protons on one of those esters, we have no reaction. So just keep that in mind. We do need those 2 alpha protons, otherwise this reaction does not happen. Now let's look for, I guess maybe we'll do one more example of a Claisen. So let me try this structure. So if we had and maybe we subjected it to this, other ester. Let's think about how this reacts. Okay, so first we have an alpha carbon. This alpha carbon of this starting ester. And of course, there are at least 2 alpha protons there, so we are good to go for this condensation. We have a sodium methoxide as our base choice, and we can just show mechanistically, actually, we don't have to show the mechanism here. I think we just showed that on the last slide. So we can kind of just go right to the product of step 1. We form that enolate. And I think it's clear that that enolate will add into this ester of step 2. And again, I'm going to do these mechanistic transformations kind of condensed, but you would imagine at first that carbon nucleophile adds into the carbonyl of the other ester. We exceed the octet, so we force those pi electrons up to form the tetrahedral intermediate. That alkoxide will then collapse and eject the methoxide all at once. So I just want to make clear here, the result of step 2 is 1 second, I'm sorry. I want to flip this upside down. So, okay, there's a 1 carbon and a benzene ring. So this is the 1 carbon and then the benzene ring. Oops, I'm sorry. 1 carbon and the benzene ring. Okay, so we formed the beta keto ester, but don't forget that that methoxide right here was ejected, so really this is the product of step 2. And that's why we need an acidic workup to reprotonate, so this is 3, to go back to the neutral beta keto ester. Okay. We did not form a stereocenter here, so we don't have to think about the major stereoisomers there. Okay, so let's consider a Dieckmann condensation. Okay, so this is just an intramolecular version of the Claisen reaction, so I don't want you to freak out. It's the same thing we've seen with intramolecular aldol, and it's actually more I guess, similar to the Claisen we just saw. So if I gave you a structure that looks like this, and I gave you this choice of base, and of course an acidic workup, what would be the products of this reaction? Well, we see we have 2 esters within the same molecule, so this is screaming Dieckmann condensation. Okay, so it's just a fancy name for the intramolecular Claisen condensation. Of course, just as we saw with the intramolecular aldol, we have to consider all potential paths that would make either a 5 or 6-membered ring. So let's start with this alpha carbon of the top ester. And if that was the nucleophile, and we had that add into the other ester, so over here, that would form a 1, 2, 3, 4, 5, 6-membered ring. So I like that. Let's call that alpha 1 forms a 6-membered ring. I like that. Okay, so let me just actually get rid of all this and then write that. Alpha 1 will form a 6-membered ring. If we look at alpha 2, and that added in to the other carbonyl, so something like this, we would have a 1, 2, 3, 4, 5, 6. So alpha 2 also forms a 6-membered ring. So we need to consider both pathways, okay, and then draw both targets, all right? So let's kind of just fill that back in. Okay, so let's start with alpha 1 going into the bottom ester. Okay, so first we can see that that nucleophile will add in, push those pi electrons up, that tetrahedral intermediate will collapse, and then eject the methoxide all at once. So let's kind of just draw the intermediate there. So again, I'm going to fill in my numbering for consistency here. We have a 6-membered ring being formed. Let's fill in our numbers. Okay, at 1 we have a pendant ester. At 2, it looks like we have a ethyl group. Keep the stereochemistry intact because we are not reacting there. At 3 and 4, it looks like we're fused with a 5-membered ring. At 5, I don't see anything. At 6 is where we have the other keto group, okay? And then keep in mind that we still ejected methoxide, so really this is the product of step 1, okay, for the alpha 1 going into the bottom ester pathway. Again, we protonate that with the second step, so really the target of this pathway is a structure that looks like this. Okay, so I think that was a really good example. Let's just try the other pathway and show how it could be a very different product that we're forming here. Okay, so if we have a alpha 2, how do I draw over this? Let me just I guess I'm just going to do this in blue. So you can imagine alpha 2 is going to add into this carbonyl, push up those pi electrons, it comes back down, ejects the methoxide. Let's fill in those numbers. So that's a 1, 2, 3, 4, 5, 6. I'm just going to draw that below, I guess, over here. Fill in my numbers. Okay, and let's kind of try and fill in, even though this is a really big mess. Okay, so at 1, we had a pendant ester, just as we did before. At 2, it looks like, and 3, we have that fused ring, the 5-membered ring. Okay, at 4, we have the ethyl group. Keep the stereochemistry intact. We're not touching any chemistry there. 5 is nothing, and then 6 is the other carbonyl. Again, the result is the enolate anion of step 1, and then we reprotonate that for step 2. So the other structure is a structure that looks like this. So notice these are very different constitutional isomers that we are getting. And if you can't see that right away, notice the position of the ethyl substituent with respect to the beta keto ester. Here, the ethyl group is quite close. Here, the ethyl group is a little bit farther away. So we get two very different constitutional isomers. I just want you guys to be prepared to draw both products on a test. So that's a good example of a Dieckmann. Now, once we form beta keto esters, there can typically be other reactions that we can do to them called enolate alkylation. This part of the exam review video is quite important because, as you can imagine, this would be quite relevant in a synthetic problem. So let me give you an example of that. So if I gave you this ester, this beta keto ester, excuse me, and I'll fill in these other reagent conditions here. There's quite a lot here. Let's talk about it. So, like I just showed you, when we eject ethoxide in a Claisen or Dieckmann, or methoxide, excuse me, any of those alkoxy fragments, the result is an enolate anion of the beta keto ester. So something that looks like that. And the reason that is that we said those alpha protons are now even more acidic than they were in the ester starting material because of a doubly or dual inductive effect. So now we can exploit that acidity, this enhanced acidity of these alpha protons. So I guess I'll say even more acidic now. We can now use a base, just like we saw before, this alkoxy base. It will deprotonate to form the enolate anion of the beta keto ester. And then if I have an alkyl halide nearby, we can now officially alkylate at the alpha position. So here we have a dibromoalkane, okay? And let me just make sure I have my number right here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Good. And in SN2 fashion, we can alkylate. So let's show that mechanistically. That nucleophile hits this electrophilic carbon adjacent to the halogen, and it displaces the bromine. So this is an SN2. And the result is we have officially alkylated at the alpha position. So 1, 2, 3, 4, 5, 6, bromine. Now, step 3 is basically exploiting the other acidic proton, so we can deprotonate there, form the anion, and then that anion can close in on itself and displace the other alkyl halide. So that is an SN2. Oops. The result of that transformation is a structure that looks like this. Okay, so that is the result of steps 1, 2, and 3. Now, step 4 is classic. This is the exam 1 material coming back. This is base catalyzed hydrolysis of the ester. So we can imagine that we're going to form a carboxylate where the ester is, the O- version. So maybe I can just erase here. This is the product of step 4. And 5 just serves as a product source to put the proton back on. So this now is the product of step 5. Well, heat in step 6, I think you can see where we're going. We have a beta keto acid here. This is exam 1 material again. And we can splice out the carboxylic acid as CO2. We get an enol that tautomerases back to the keto. So the result is a structure that looks like this. Oops, I'm running out of space. Here, let me just redraw this. Oh, excuse me, I just realized I dropped a carbon, so let me just have done this. So remember, it was a 6-carbon fragment. If I were to count my carbons here, 1, 2, 3, 4, 5, I dropped a carbon in my ring. So let me just make sure I also didn't do that here. 1, 2, 3, 4, 5, 6, yeah. So the result of this intramolecular is not quite that. Let me just fix this for you so I don't have to make another video, but something that looks like this. So 1, 2, 3, 4, 5, 6. Perfect. Okay, and then again, you can imagine that this group just goes away when we decarboxylate, and we're left with that end product. Okay, this is the end product. All right, make sure you count your carbons. Don't ever drop carbons. All right, so I think that's a good stopping point for Claisen and Dieckmann condensation. The next video will pick up, I guess I'm going to do a separate video now, on the Michael addition and the Robinson.